My great pleasure to introduce my colleague, Professor Francesco Volpe. Francesco used to be a professor of plasma physics at Columbia University in the US, when he realized that he would have a lot more fun starting a private company and making fusion power a reality. He's now running one of the few, I believe, 3 fusion companies that are private fusion companies in all of Europe. And he's specializing on Stellarators with liquid walls and high temperature superconductors. And he will talk to us today about the technology behind his company and hopefully also a little bit about his company. I'm excited about this because I believe that if we can solve the problem of having cheap energy with little impact on the environment, that will make many of our other problems go away. And I believe that fusion power eventually is the solution, or at least part of the solution for this. So let's see what Francesco can tell us about it. Thank you very much. Off you go.
Thank you very much, Ralph, for the introduction. It's a big honor to be here. We were joking over lunch on the fact that with my high school professor, he wanted me to become a mathematician. And I never dared to tell him I wanted to become a physicist. And eventually I became an experimental physicist. And I do fusion, where I work at the boundary between physics and engineering. And most recently, I became a sort of businessman. So my descent, to lower and lower grades was complete. But jokes apart, there are a lot of interesting theoretical, mathematical, and physical problems that I would like to share with you today. Let me go back to the first slide. That I would like to share with you today, that hopefully will be inspiring, hopefully will prompt new collaborations, or will inspire some of the students and postdocs in this audience and in the remote audience to join this endeavor. As Ralph said, the company is called Renaissance Fusion. It's located in Grenoble, France. We are a very international group. At the moment, we are 18. You see 14 of us here, and 4 more just joined recently. In fact, we are in a moment of significant expansion. We are growing to 60 people by the end of the year. And again, I cannot stress enough this point about the fact I'm looking for talents. We are looking for talents. So in this presentation, I will give a brief reminder on fusion and plasma confinement, a motivation on why fusion and why specifically our approach to fusion, our 3 pillars, as I call them, on high temperature superconductors, liquid metals, and stellarators. Let me show you, let me use this mouse. Yes, here we go. Recent results and next steps. So first, a quick reminder on fusion. The reactions used in the sun are shown. Sorry about this. Just familiarizing with the mouse. Here we go. The reactions used by the sun are shown here at the bottom left, relying on the weak nuclear force. And you see plotted, apologies. And you see plotted on the right, the fusion reactivity. If you multiply this quantity by the densities of the 2 reactants, you obtain the number of reactions per unit time and unit surface. You see this quantity plotted against the temperature of the ions for various reactions shown here. The reaction happening in the sun has very low efficiency. Very few reactions take place per unit time and unit volume. Yet the sun is producing a huge amount of energy per unit time. On Earth, we need to do something more compact, so we rely on other reactions, one of which, the most often used in today's laboratories, is the fusion of deuterium-deuterium with a branching ratio of 50% in these 2 families of products. You see the reactivity of this reaction in orange here, much more effective, several orders of magnitude more effective than proton-proton. But even better than that, and what we want to use in reactors, in actual power plants, and what has been used in some experiments in the past and will be used in a few years by ITER, the large tokamak under construction in Provence, an international collaboration you might have heard of. That reaction is deuterium-tritium, giving an alpha particle and a neutron. You see here the reactivity shown in blue, much higher than the others. The tritium for this reaction is sourced by the same neutrons that are produced in the reaction, reacting with a blanket of lithium and producing indeed tritium, which is reinjected in the plasma infused. This is the good part. The neutrons carry the heat, most of the heat, 80% of the heat, and we want to capture them to extract this heat indeed. But at the same time, they create issues in terms of activating the solid part of the reactors, which is why other public and private endeavors try to exploit other reactions shown here in green, in purple, and in red. Less efficient, but they have the attractive feature of producing fewer or no neutrons at all. In reality, at Renaissance Fusion, we have a solution by which we can deploy the deuterium-tritium reaction without the disadvantages of the fast neutrons, as I will show later. Now, if you noticed the numbers in these slides, you saw MEV with a capital M all the time. This is the energy produced in every single reaction, as opposed to MEV with a small m, with a lowercase m, or EV produced in chemical reactions. So this is the reason that makes fusion so energy dense, and this is why we need such tiny amounts of deuterium-tritium fuel to produce the equivalent of many, many barrels of oils or many carloads of coal. It is also, by the way, very efficient in respect to power per unit surface, unlike, for example, solar. So we want many reactants, as you see on the left. So of course, we want high density of reactants. You want these reactions to take place, and before the strong nuclear force prevails, you have to defeat Coulomb repulsion. So you want this nuclei to collide at high energy, which is why you want high temperature. And last but not the least, you want to make an efficient use of this heat, both externally injected as well as internally produced by fusion reactions. Because at the end of the day, what matters is the temperature, but what you're spending for is the heat. And just like in your apartment, you care about the temperature, but you want an efficient heating system. You want to spend little heat, and therefore you have a small electricity bill or gas bill. In a fusion reactor, it's exactly the same. You want to well confine your energy. So you want good thermal insulation or good energy confinement, which is why I'm sketching the system as a closed or nearly closed system with very modest leaks of energy. This can be summarized by the requirement that we want a high product of these three quantities: density, temperature, and a metric of confinement called energy confinement time, the time scale over which energy leaks away. For deuterium-tritium, you need to exceed this threshold for net energy to be produced. The threshold for other reactions is even more challenging. A typical power plant will consist of a plasma, most likely deuterium-tritium, producing these neutrons, interacting with a blanket of lithium that produces the tritium, which is reinjected in the plasma. This blanket of lithium becomes hot under neutron bombardment, and this heat can be extracted by a heat exchanger. This is basically a furnace, so it's the core of any thermal power plant, be it coal or fission, which is in fact very interesting. It offers opportunities of retrofitting coal power plants, fission power plants, something we are looking very actively in. And in the value chain of fusion, even though the ultimate goal is to produce electricity, net electricity, for which when all the losses of the power plant from the previous slide are factored in, you need actually to produce much more heat than you inject, again, to compensate for losses. So for net electricity, you need a fusion gain of 20 times heat out, more heat out than heat in. But at capital Q fusion gain of 5, so no net electricity, but net heat, you can already do very impactful things in terms of, for example, producing green hydrogen or decarbonizing some industrial processes which are very heat intensive. So production of paper, steel, glass, cement, etc. One step back, with very modest amounts of fusion gain, just a small amount of fusion neutrons, fast neutrons, you can produce scarce medical isotopes or treat fission waste. And one further step back, this is magnetic confinement fusion. The magnets that we are developing for fusion are large, very accurate, and strong. They generate strong magnetic fields. These three requirements are encountered also in other fields from energy storage to medical imaging. So there is an opportunity to make something good for society, and in the case of energy storage and wind energy and mobility for the environment, before even making any net fusion electricity. So, as you saw before, we need to exceed this threshold in triple product. If you remember the plots on reactivity, there is an optimal temperature at which to operate of the order of 10 kiloelectron volts. So in reality, our knobs are the density and the energy confinement time. There are three main approaches to fusion. In one, inertial confinement, you push this knob very hard. You work at very high densities, higher than solid. You compress basically a capsule of fuel by lasers or other means until exceeding the triple product threshold. On the opposite end of the spectrum is magnetic confinement, in which we act on the energy confinement time. We maximize that by confining the plasma with strong magnetic fields and or by making the device large enough. This increase in size relative to the Larmor radius maximizes the time spent for particles and energy to travel from the core to the edge of the plasma and eventually be lost. What is interesting now, as you will see later, is that now we can make the Larmor radius much smaller thanks to strong magnetic fields. And it has just the same effect in a wind tunnel spirit as making the device larger, but is more. Yes, the energy confinement time is the time scale over which the energy is lost from the system from the moment you turn off the heating systems. So if we suddenly turn the air conditioning in this room, it will take some time for the temperature to stabilize to a new value, a certain time scale, the same in the plasma. It is dependent on the density, because among other things, it depends on collisionality and on turbulence, and both processes depend on density. So indeed, yes, it is a function of density and other things, the magnetic field, the helical twist of the magnetic field. Yes, this is a simplified picture, but very good point. Thank you. So the magnetic confinement, between magnetic confinement and inertial confinement, you have the hybrid of magneto-inertial, in which, as the name suggests, you magnetize a plasma and compress it, as you would do in inertial confinement, trying to get the best of the two worlds, or the worst. We focus on magnetic confinement because it's the process that has approached more closely Q equal 1, capital Q equal 1 net heat. And there are two champions in this field of magnetic confinement called the tokamak and the Stellarator. They are both toroidal devices where magnets pictured in blue, coils pictured in blue, confine a plasma shown in purple, a toroidal plasma. The field shown in black is helically twisted. At the first proposals of toroidal confinement of a plasma by magnetic fields, Fermi immediately realized that due to the 1/r, r being the major radius, non-uniformity of the toroidal magnetic field, the Larmor radii will also be non-uniform, and this will result in a vertical drift of charged particles, the positive ones in one direction, the negative ones in the other. Your particles are lost due to this radial non-uniformity of the toroidal magnetic field. The solution to that is helically twisting the magnetic field. This property is called rotational transform. And the difference between the tokamak and the Stellarator is how you impose this twist, this rotational transform. In the tokamak, there is a solenoid acting as the primary of a transformer, and your plasma is the secondary of the transformer. So a current is induced in the plasma, shown here in the toroidal direction, that generates a field in the poloidal direction, and hence the twist. On the other side, instead, we have the Stellarator, where the same is obtained by deforming the plasma, by helically twisting the coils, and thus the plasma, and ultimately the magnetic field. In the tokamak, the disadvantage is that even though, in spite of the apparent simplicity of the coils, this current is inevitably pulsed. You have a linear ramp of current in the primary to get a constant current in the secondary, and you cannot make an infinite linear ramp. So inevitably, this device is pulsed. You can make long pulses of half an hour or so, hopefully longer, but it's pulsed. Secondly, it is unstable. We are talking on a very large current, resulting in very large current-driven magnetohydrodynamic instabilities. The most dangerous of which is the disruption, a sudden loss of confinement in few milliseconds. The energy that you have accumulated in seconds is suddenly lost in few milliseconds, with consequences for the device and possible regulatory issues. Instead, here, the way a stellarator works is everything is DC. You turn on your coils, you evacuate your vacuum chamber, you inject a gas, deuterium tritium, you ionize it, you inject enough heat to warm it up to fusion temperatures, and voila, you have fusion energy. Everything is steady state. So everything is simple to operate. In fact, it's also very energy efficient because you don't need so-called current drive methods to non-inductively sustain the current, as instead you do in the tokamak. The disadvantage of the stellarator, and the one we address at Renaissance Fusion, is these coils on the right are more complex than the coils on the left. And in modern stellarators, they are even more complex, more difficult to build. So we came up with an idea that simplifies that. But before doing so, a quick comment on the energy confinement that the colleague was asking about. A quick plot just to show a couple of things. First, experiments agree with theoretical prediction. So theoretical expectations and measurements of this energy confinement time are in good agreement. The data points lie on the diagonal. And the data points from tokamaks in gray are clustered together with the color points for stellarators. Tokamaks and stellarators of the same size and magnetic field achieve comparable confinement without the disadvantages like these disruptions I was referring to. Now, the motivation for what we're doing, Renaissance Fusion and in general in fusion, is that even though I'm a big supporter of renewables, renewables are not the only solution to the problems we are facing in our society. Renewables, I used to live in Manhattan, and this is the amount of power consumed per unit surface continuously, the city that never sleeps. This is the amount per unit surface produced by a farm of wind turbines intermittently. So there is obviously a discrepancy here. And about energy storage, with your cell phone is powered by a lithium-ion battery, your laptop, your car, but seasonal storage of energy for a city of several million inhabitants, unless we find a completely different solution, that problem is not solved yet. This is how much energy needs to be stored for 24 hours for 1 million people city, comparable to a nuclear bomb amount of energy. And by comparison, this is the output of a gigafactory of ion batteries per year. So again, another discrepancy. Fusion, the energy of the stars is the solution to this and to several other problems. Apologies, the fonts from one computer to another got messed up, but yes, there are several advantages all shown here. From geopolitical advantages to safety compared to fission, for example, abundancy, fuel efficiency, land efficiency. One advantage that is not underlined well enough, in my opinion, is the ability to follow the demand of energy from society, as opposed to, for example, just provide a base load. So we hear this term continuously, base load. So that's when you turn on a power plant and you keep it on at a fixed level of output power with minimal changes or none at all. Fusion can certainly do that, but even better, it is a load following power source, meaning that if there is a fluctuation in demand, it can respond on a time scale of the energy confinement time, few seconds, it can respond with a fluctuation in supply. Now, we live exciting, definitely exciting time, someone would argue expensive times, because after a long progress from the 60s to the 90s in that triple product that I was mentioning before, and correspondingly in the fraction of output heat to input heat, shown here on the right, After so much progress, now we are approaching this elbow here in this dependence on one upon the other. This is ITER, the large tokamak, international tokamak I mentioned before. Exciting, but the expensive part is that to get there, you need large devices costing tens of billions. The role of the startups, like Renaissance Fusion, is to recalibrate this horizontal axis, try to build for billions what was previously built for tens of billions, which, by the way, was out of the scope of public labs. The mission of ITER is to prove the scientific and technical feasibility of fusion. It was not, and it is not to address its economical feasibility or attractiveness. This is where startups can play and should play a role. Combined with the acceleration to reach markets for fusion, which are not just electricity, but as I showed before, heat or medical, for example. So there is a lot of excitement around fusion at the moment, and fusion startups in particular, due to a combination of three factors: an obvious need, good enough technical readiness of fusion, good enough for starting industrial research and development, and breakthroughs in related fields as magnets, computers, and lasers. And one message here is, if we want to contribute to carbon neutrality by the 2050s, we need to start commercializing by the 2030s. There has been an explosion of startups. You see the timeline here. We are the last one in this timeline, the most recent, but we are catching up quickly thanks to good ideas and good people. And you see on the right papers from specialized journals as well as mainstream journals excited about fusion. There are about 35, actually nearly 40. They keep appearing one week after another. I need to update this slide. Nearly 40 companies all over the world, distributed geographically as shown by these columns and technologically as shown by these rows. These rows are ordered by readiness, with the tokamak being the most ready and the Stellarator admittedly the second most ready for historical reasons, related once again to the complexity of the coils, but catching up if those are resolved. They can be grouped into two large families: concepts that are working and companies are working to make them cheap, or concepts that are cheap and people are trying to make them work. We prefer the first approach. Working means developing prototypes. In our case, since we started very recently, we are, as I will show in more detail later, we are focusing on two enabling technologies: superconductors and liquid metals. But these companies are actually building devices, are not, you know, only making designs, or they're actual machine builders. Maybe I will take one more second to expand the answer, to say that one thing is building the experimental devices, another is operating the experimental devices. That's an area in which I believe, in fact, I strongly believe these companies should work very closely with public institutions. And let's say we are taking steps in those directions of building machines and then operate them jointly with public institutes. So, of the companies pursuing the deuterium-tritium reaction, which is once again the most efficient, three are pursuing the deuterium tokamaks or Stellarators. Ourselves in Europe, Commonwealth Fusion Systems, a spin-off of the MIT, on the tokamak, and the tokamak energy working on the spherical tokamak in the UK. But we are indeed the only one working on the deuterium-tritium Stellarator with all the advantages listed before. As we go down in that funnel, I listed the advantages, but there are also challenges that we need to face as we go down in that funnel. So fusion neutrons from deuterium fusion can induce radioactivity in the solid parts of the reactor. We address that by coating the inside of the fusion reactor with a layer of liquid metal, a solution containing lithium, that absorbs most of the neutrons before they reach the solid parts of the reactor and make them radioactive. Tokamaks and stellarators tend to be large, but we address that by strengthening the magnetic field. At the end of the day, again, it is the ratio of the Larmor radius to size that matters. And stellarators tend to be complex, as you see in the cartoon on the left, but I will present a technique that greatly simplifies that and at the same time, the HTS manufacturing process. So in a way, we think we're making the Stellarator safer, smaller, and simpler. So let's start with simpler, specifically simpler HTS manufacturing. The traditional way of making high temperature superconductors is by means of tapes, similar to audio cassette tapes, for those of you who remember audio cassette tapes, like myself, traveling back and forth in various machines where they are coated with various layers. The one in black is the superconducting one, the others have electrical, mechanical, protection properties. After this tape has been produced, several tapes are stuck together and helically twisted into a cable, which is wrapped on a non-planar table to produce a non-planar coil for the Stellarator. And finally, the coils are carefully positioned around the fusion device, the vacuum vessel. So both this manufacturing and positioning process require accuracies below a millimeter. I was going to say, yeah, thanks for that's good, by the way. That's we are aligned. We're tuned. Okay, I was going to say that these devices are few meters in major radius, and yet you need these coils to be manufactured and positioned with the sub-millimetric precision. So instead, what we do is we skip altogether the concept of tape and cable. In a way, it's like skipping altogether the concept of transistor and making an integrated circuit. So what we do here is directly deposit the HTS material on a cylinder in just 2 machines as opposed to 7. As a matter of fact, we deposit a stack of many layers of HTS intertwined with the other layers that I mentioned before. This multiple stack is our equivalent, more elegant, I would argue, of winding multiple times the tape or the cable to make the coils. We just deposit multiple layers, one on top of the other. The result of this deposition process is a cylinder that superconducts in any direction, which is not what we want in reality. What we want is specific current patterns that generate the specific magnetic field geometry needed for Stellarator confinement. So what we do is with a laser, we ablate this cylinder in specific locations. Effectively, we make grooves in the cylinder. These grooves bound the current. When you energize these coils, the current will follow a specific pattern as imposed by the boundary conditions by these insulating grooves. One point I would like to stress, there is superconductor nearly everywhere except then in the grooves, not the other way around. These are not current filaments, these are current stripes bounded by narrow grooves. Once these cylinders are ready, and by the way, please notice that the 3D sculptures from the previous slide are now replaced by 2 1D movement, a rotation of a cylinder and the translation of a laser. And finally, the cylinders are shipped to the power plant manufacturing site and assembled all together to form a torus, which is at the same time the cryostat, the vessel, and the coil set. People are interested, I have a video on details of this process, but in the interest of time, I will move on and comment on why this is also a simplification of the Stellarator. So historically, the coil winding surface, so the surface on which these coils have been designed, has become more and more complicated, as you see in this illustration. The point is that we want to accurately generate the magnetic field that confines the plasma in yellow. And if you choose a conformal coil winding surface, conformal in the sense of parallel to the plasma boundary, and you stay close enough to the plasma, this is typically considered to be good. You don't want to be away from the plasma because high-order multipoles decay more rapidly. And for the same amount of plasma shaping, you need more coil shaping. This effort of staying close to the plasma, I think we have overdone it. We have made our life unnecessarily complicated, in the sense of we have chosen, we came into the paradox of adopting a complex surface in blue, and then on that surface simplify the current pattern. So here comes the idea, why not do the opposite? Let's adopt simple surfaces. We know already that the patterns on those surfaces will be more complicated. We expect that already, but who cares? It's just, it just means that the programming of the laser will be a bit more complicated. The trajectories will be more zigzaggy, so to say, to yield the same results. And this is a proof that this is indeed true. So the plot on the left and the plot on the right correspond to the two configurations on the left and on the right of the previous slide. Shown on the vertical axis is a metric of coil complexity. Indeed, if you adopt a piecewise cylindrical envelope, you obtain higher values in this metric, a more complex pattern compared to adopting a conformal surface. But the point here, the important message here is that this level of magnetic field accuracy, 1 part in 10 to the 3, is sufficient to build a satisfactory or more than satisfactory stellarator. There is also another aspect, which is flexibility with respect to the distance between the coil surface and the plasma boundary, giving enough space for that neutron shielding and tritium breeding of liquid metal. And last but not the least, a code has been recently published. It is actually already published on a journal, but the preprint is available on archive in collaboration with our mathematician friends in Paris and Strasbourg, by which now we will optimize the coil-winding surface. These cylinders were geometrically constructed, but if you now start moving left or right or elongate or otherwise deform the cylinders, we expect to achieve even higher accuracies of the order of 1 part in 10 to the 4. And in fact, we think that the best results will be obtained if we have a prism of non-circular cross-section and extruded non-circular cylinder as shown in this picture on the right. Stellarators are made smaller by the... Please, of course. Four or five slides ahead, I will give you the answer. Thank you. So stellarators are smaller thanks to the strong magnetic fields. So this is how much the size reduces, shrinks. If you increase the magnetic field from 5 to 10 Tesla, the major radius reduces as such. I should clarify, however, that this is also made possible by the lower aspect ratio. So making a plasma which is fatter, basically, the aspect ratio is defined as the ratio between the minor radius of the torus and the major radius of the torus. That's also important. A topic which I hope will be of interest to this audience is that we can, for a given target field in the volume and for a chosen surface, coil winding surface, there is only one exact solution of current on that surface, exactly giving that magnetic field. But there are many approximate solutions of current on that surface. And out of these many approximate solutions, we can choose the one that strikes a good compromise between field accuracy, coil complexity, and this is new, force minimization. This is something that was not studied in other stellarators before because they were operating at lower fields. But if now, thanks to high temperature superconductors, we go to 10 Tesla, let's say we double the field, in principle, we quadruple the forces if we don't change anything else. In reality, actually, compared to present experiments, we are quadrupling the field and therefore, in principle, going up in a factor of 16 in forces. Again, if we don't change anything else. But based on this fact that there are many approximate solutions, you can properly define an optimization metric and a force minimization metric, a force metric, Laplace force metric, either surface, the surface average of the root mean square, Or you can introduce a nonlinear penalty. Basically, forces below some value are allowed, between a soft and a hard limit are penalized, and above a hard limit, the penalty is infinite, so the forces are completely forbidden. If you do that, you can achieve a good compromise shown in the third column between simplicity of the coils. You see that this current pattern is simpler than this one. For example, this is the current shown in an unwrapped surface of the torus. So poloidal coordinate here, toroidal coordinate here. Good field accuracy, so small field error shown here, and lower forces. These forces here are a factor of 2 lower than here. So also helping in our roadmap to smaller stellarators. Regarding the question about the HTS being damaged by radiation, by neutrons, by heat, and not only the HTS, by the way, the vessel itself, we protect both the HTS and the vessel by means of liquid metal walls. These are walls of lithium-lithium hydride, as shown in the next slide. The MHD, the simple physics that allows us to have it stick to the wall is that in this the liquid metal is injected from the top and is forced to flow along the surface by means of J cross B forces pushing radially outwards. Remember, we are in the presence of a strong B, so just applying a current in the liquid metal by means of electrodes in proper direction gives you forces pointing upwards. At the end of the day, it's parallel currents attract each other. You have these parallel currents in the HTS coils on the outside. You have parallel currents in the liquid metal, which is a deformable medium on the inside. The currents on the inside tend to move towards the current on the outside, and so the liquid metal tends to stick. Either by, and it does so better and better if you increase the force and or the electromagnetic force and or the velocity, and thus the centrifugal forces.
Ready?
And in this animation,
Three,
in this
two,
video,
one, decrease.
this video, you see a liquid metal flow sticking to a substrate. That was me laughing like a maniac.
Ready?
Yes.
So when you turn off the J
one,
cross B, the
decrease.
liquid metal flow detaches from the substrate. This is a 1 centimeter thick flow of gallium indium tin, a convenient material for experiments at room temperature because it is liquid temperature. It is not what we want to use in the plasma. In the plasma, instead, in contact with the plasma, we use lithium. Before I describe our lithium solution, a quick word on stability. It is inevitable to be concerned about this lithium, this liquid metal flow, about eddies that can develop in this flow, droplets that can develop in this flow, regions of depletion. So to contrast both the depletion and the bulging of the liquid metal to stabilize effectively Stellarator, Kelvin-Helmholtz, and other instabilities, we have a simple solution, which is an array of electrodes immersed in the liquid metal, by which, simply by controlling the potential of these different electrodes, we can design the current pattern in the liquid metal such that in regions where the liquid metal is bulging, we apply a slightly stronger J cross B. In regions where it is depleting, a slightly weaker J cross B. This is an idea, by the way, inspired by what we do in plasmas. When the plasma is bulging out, you apply a correction with a magnetic coil. That non-axisymmetric correction coils used at Columbia for this purpose. And so that's exactly the same thing with a different actuator, electrostatic as opposed to magnetic. Now, our material is a solution of lithium-lithium hydride. So lithium is needed for the breeding of the tritium, as you saw before. And it's a very good absorber of neutrons at low energy, but a very lame attenuator at high, medium, and low energies. So if you follow the history of a neutron in a layer of lithium, what happens is that a long distance is traveled for the neutron to gradually slow down, and finally, in few centimeters, the lithium is absorbed. We are asking, or they, other people are asking to one material to do two different jobs, but this material is only good at one and not at the other. So there is a reason why they use water in fission reactors, hydrogen. So protons have comparable mass to neutrons. They are much better attenuators by collisions compared to lithium. In fact, they have a cross-section 80 times higher than lithium. So they are 80 times better than lithium at slowing down these neutrons. Hence the idea of, instead of just lithium, use a solution of lithium hydride. Okay, much more effective at slowing down the neutrons, as I said. And eventually the lithium absorbs them and produces the tritium. Although hydrogen is a good attenuator at medium and low energies, you need an additional material to moderate at high energies. This is which serves a dual purpose. It also multiplies the neutrons. So there is an N-to-N reaction. And this is important because some of the neutrons will escape from the reactor. But if we really want to make a closed loop, where for each reaction in the plasma, we produce a triton, which is reinjected in the plasma, we need to compensate for these neutron losses. So you need a neutron multiplier. The lead does just that. And this layer of materials protects, back to your question, sir, protects the superconductor from damage by neutrons, from nuclear heating, etc. This is important, of course, because the superconductor relies on a precise crystalline structure for its superconducting properties. If these foils of copper oxide alternated with yttrium and barium are damaged, the superconducting properties are lost, or at least degraded. It is not super clear from the sketch, but this layer of lead, which seems to magically float on top of the lithium hydride, is in fact a granular fluid, is in fact ball of pebbles containing lead, which at those temperatures is molten, but the outside of the pebbles is solid, and it is a ceramic, which is electrically insulating. And so what happens is when we apply our current to the liquid metal, these electrically insulated pebbles are not subject to the J-B force pushing outward. So instead, they tend to accumulate inward, where they are most needed, both for the attenuation at high energy and for the multiplication. This choice of materials in a relatively modest thickness of 46 centimeters allow us to attenuate, to absorb 99% of the neutrons. So only 1% of the neutrons passes through, and a much smaller fraction of the neutron energy passes through. This is the energy spectrum of neutrons as a function of distance traveled across this medium. There is an additional advantage. This solution of lithium hydride also allows us to extract the tritium. So shown on the right is the phase diagram of a solution of lithium hydride, concentration on the axis, temperature on various phases. And lithium hydride, deuteride, and tritide are chemically very similar to each other. So this is in fact a concentration of hydrides, plural. Inject the liquid metal at 700 Celsius in the device. Under neutron bombardment, it warms up to 900 Celsius. You extract it from the stellarator. Before re-inject it in the stellarator, you want to remove the heat, which you do by heat exchanger. Basically, you cool it down. In the process of cooling it down, you can also extract the tritium. Why? Because you make a phase transition to this phase here, where there is a precipitate rich in hydrides, including the tritide. And if you do it carefully, as a matter of fact, similar to a distillation, you can extract just the lithium tritide, because there are slight differences in precipitation hydrides. So as an intermezzo, and probably nearly the end of my talk, as a matter of fact, because I'm not doing too well with time, this is a symbiosis between the three ideas, in which this is not just a random collection of three ideas. They really work very well together, and they help each other, and they are symbiotic to each other. And without entering in all the details on this triangle, I will just say that the strong field generated by the HTS helps the liquid metal stick into the wall. And on the other hand, the liquid metal protects the delicate HTS. Similar synergies exist by Stellarator. I should also mention that regardless of our approach succeeding or not, liquid metals and HTS are good for fusion in general. These are some pictures from other companies working on fusion, various magnetic inertial approaches. Most of them, nearly all of them, in fact, need HTS. Advances in these areas are important for the whole field. Just few quick words on recent progress, for example, in Stellarator theory, in obtaining equilibrium between the kinetic pressure that tends to expand the plasma and the magnetic pressure that tends to compress it, for non-axisymmetric configurations of aspect ratio of unusually low aspect ratio, between 3 and 4, so fat plasmas basically. So these are small in major radius, but they're fat in minor radius. This is exactly what you want for a compact reactor. You can see, by the way, the shrinking from standard designs. So this is by a factor of 5 or so, as you see. Equilibria obtained by our Stellarator equilibrium theories that also exhibit high rotational transform, that properties that I was describing before. Low effective ripple. This is a metric of classical transport, so transport in toroidal configuration. So it's really a very promising configuration, and there is a similar one shown here for 3 periods as opposed to 4, which you saw in the previous slide. Yes. Are numerical results, yes. So I was a bit fast, but these are numerical results. And the color contours are contours of magnetic field strength on the last closed flux surface. So compared to, so we took the HSR3 stands for helical axis Stellarator reactor. 3 stands for the number of periods. And this is a design, one of these gigantic designs that I showed in one of the original slides. Gigantic if you do it at low field. If you do it at high field, so you see the field much higher here than here. Other mouse, this pointer. If you here much higher than this one, that allows to shrink by significantly. For completeness, these other contours on the right, this is the field strength, again on the last closed surface. Basically, if you take the torus and you unwrap it, and you plot the field strength as a function of the poloidal and toroidal coordinate, you get these nice stripes. So this is a quasi-isodynamic stellarator, which basically means your particles, even where they are trapped between maxima of magnetic field, are not drifting away from the plasma. They stay close to it. And at the same time is quasi-helically symmetric. So the field patterns as a function of the toroidal and poloidal coordinates. Are both properties that yield good confines. When it looks like that, when it looks like stripes, it's a good sign. Alpha particle losses, so the alphas that we produce in the deuterium reaction, is that we want them to stay in the plasma. So the idea is 80% of the energy goes in the neutrons. We capture the neutrons. They are obviously not subject to the magnetic field, not confined by the magnetic field. The alphas are confined by the magnetic fields. And that's good because it means 20% of the fusion energy stays in the plasma and keeps it hot for more reactions to take place. Basically, we don't have chain reactions in fusion, at least not mediated by neutrons, but we have a sort of chain reaction, not quite, but one reaction can promote the next one because part of the heat from that reaction keeps the plasma hot and fosters more reactions. So it's heat mediated rather than neutron mediated. So bottom line, we want the alpha particles to stay in the plasma. And so an important calculation is what is the fraction of alpha particles lost as a function of time. And the device that I showed before, the one in red, exhibits comparable trajectories with other mainstream devices. There is a new quasi-axisymmetric configuration recently generated by a colleague in Maryland. And so the next thing we will do is take that and scale it up in field size for recipe. But the point is this performs just as well as traditional devices. Another interesting development is optimize the number of parameters to describe these complex surfaces. And so normally you need something of the order of 400 Fourier coefficients. But a colleague is working with a colleague at Renaissance Fusion is working with other colleagues at Princeton to develop a machine learning artificial intelligence method that, based on this input, it encodes and distills only between 40 and 100 coefficients to reproduce the same equilibrium. It's important because when you optimize, when you look for plasma shapes that better confine your plasmas, you don't have to move away in a 400-dimensional space, but only in a 40-dimensional space. And yes, I know at first sight it might be counterintuitive, but let me go back one slide or two. So the poloidal and toroidal coordinates shown here are in fact Boozer coordinates, as we call them. They are not exactly the toroidal and toroidal coordinate in the lab frame. They are combinations of them. Basically, it's a curvilinear coordinate system that you can define on this tori. If you properly define your variables, the system is in fact axisymmetric or quasi-axisymmetric, or more generally quasi-symmetric set of coordinates. So in these three, if you don't think in, again, the lab frame coordinates, but you think in these other coordinates, major radius, quasi-poloidal, quasi-toroidal, also called Boozer coordinates or magnetic coordinates. In this set of coordinates, the stellarator is actually bidimensional. One of the three dimensions is ignorable, just like in the tokamak, the toroidal coordinate is ignorable. So they don't look bidimensional to our eyes, but in a proper set of coordinates, they are bidimensional. This bidimensionality lowers the dimensionality of the system, improves transport, and gives good confinement. So they don't need to be two-dimensional in the lab frame. The advantage is better confinement. I don't have it in this presentation, unfortunately, but I can explain in words and maybe send you more references later. So I alluded briefly to the effective ripple. That's a metric of transport. Neoclassical, well, sorry for the jargon, collisional transport in toroidal geometries, neoclassical, as we say. So on the net of turbulence, which is a whole other class of, nuances, but on the net of turbulence, if you just think about collisional transport in toroidal configurations, modern stellarators are actually better at confining the plasma than tokamaks. Again, counterintuitive at first sight, but if you try to calculate this metric, which is called effective ripple, it is actually lower in a stellarator than in a tokamak. Quick memories. Can I make a sketch quickly? Okay, so if you plot the field strength, the function of the coordinate along the field line, so this field line is helically twisted, right? So it moves from the inside to the outside of the plasma, and in doing so, it moves between region of high and low magnetic field. Okay, so a particle moving along the field line experiences maxima and minima of magnetic field. Okay, and therefore maxima and minima of magnetic energy, potential energy. If there's enough energy to pass, it will keep moving along the field line. If it does not, it bounces back and forth between turning points. It's trapped. Exactly. That's exactly, it's the particle is trapped. That metric, epsilon effective, to the power of 3/2, it's a metric of this trapping. It's a metric of the ripple in that field line. And although it's counterintuitive at first sight, you can make it smaller in a stellarator. In a stellarator, the physics is much richer, is much more complex, because in addition to 1/r dependence, so that gives you a kind of, slow variation along the field line. So if you have, I don't know, if your field line helically twists 3 times, you have 3 minima and 3 maxima. Okay, but exactly, because in a stellarator, you have, due to the complex shape, you have additional maxima and minima. You have at least 3 or 4 families. So there are many. So there is a slow, medium, and short length scale, by the way. And if you look at the details of particles globally trapped or locally trapped, actually these, if properly optimized, can be better than the tokamak confined in the plasma. Now, I believe there are many, well, I'm sure there is a fraction of high energy particle physicists in the audience or remote audience. So I would like to stress that HTS can be very good for accelerators. And actually we have a collaboration with the synchrotron we are starting a collaboration with the synchrotron in Grenoble. So one quick step back is that if you different field geometries for different applications, medical, energy storage, etc., that technique that I showed you before just requires different corrugations. So for different B, you need different corrugations, okay? You can even do tapes if you want. You just cut all the way through the cylinder. And some of these applications are useful for accelerators. One idea, for example, is to deposit the HTS on the beamline, directly on the beamline, pattern it, and by different patterning, you can do quadrupole, hexapoles, octupoles, bending magnets, you name it. In particular, we are excited about taking plates and patterning them with serpentines, as shown on the left, which coincidentally is also an energy storage concept. So when a colleague from the synchrotron saw that, he said, "Oh, that's an ondulator." So for wigglers, sorry, it's an ondulator for synchrotrons. And it turns out, but I will not enter into too many details because I think I'm nearly done with my time. It turns out that only with this technology, our technology, you can generate very strong fields on short distances. Typically, these two things are mutually exclusive, but in a good ondulator, you want to let's say aggressively bend the trajectories of your electrons, but for reasons of coherent sum of your X-ray signal, you want to sum up over several periods. Therefore, for the same total distance, you want many short periods. Long story short, with our technology, this is possible. And here you see that by operating at 20 Kelvin, you can generate fields of 1.2 Tesla without getting too close to quenching. So superconductors can be, as you know, a big deal if your superconductor suddenly loses superconductivity. And by operating at lower temperature, it can safely superconduct up to 1.5 Tesla, and yet be oscillating on just 1 centimeter. Yeah, I'm not sure I have the time to enter in details. Maybe one quick comment about the fact that in addition to the main corrugations that gives you, this is a piece of the serpentine, by the way. So you have to imagine this mirrored and periodicized. So if you now do grooves inside the serpentine, you avoid points of accumulation of current. Current in superconductors takes shortcuts just like in regular conductors, of course. It's a different type of shortcuts. They don't take the pattern of minimum resistance because resistance, the path of minimum energy, which sometimes is counterintuitive, but they tend to accumulate at they tend to cut corners. Slalom as closely as possible and accumulate at these locations. And you can reduce that by properly guiding the current with proper grooves inside the main path. And also another trick which our colleagues are very happy with, we added an ion yoke top and bottom of the superconductor. So now the ion tends to attract the superconductor. The two serpentines tend to attract each other, but strategically positioned ferromagnetic materials top and bottom attract the superconductors in the opposite direction. If you properly design it, these superconductors stay in place. You get balance of forces. One final slide or two, and again, I'm sorry, this is a bit over time. Can I just 2 slides? Okay. Our roadmap. So for the first 3 years, our main focus, experimental focus, is building and demonstrating a cylinder 1 meter in length, 1 meter in diameter, externally coated with HTS with that technique that you saw before, and internally coated by a flowing layer of liquid metal, 20 centimeters initially. Because this will be the building block to build first a small, then a medium, and eventually a large Stellarator, as we learn to make bigger and bigger cylinders. As you saw, this technology, whether planar or cylindrical, has also spin-offs in accelerators, energy storage, and other applications. In parallel, we are, as you saw, from those equilibria that we were discussing before, we are designing our plasma shape, and correspondingly, we need to solve the inverse problem of, given this plasma equilibrium, what is the pattern of grooves that heals, bearing in mind all the superconducting physics of minimum energy path, which, as I said, so that's an important design and modeling work that is being carried out in parallel with these 2 experimental activities, so that when we are ready to build a Stellarator, we are ready also with a design for the Stellarator and an optimal plasma configuration that we want. So part of the reason why I'm here is to look for talents who might want to join us. And this is a list from the department head to group leader to physicist level. And these are some emails, a web page when you can consult openings. Quick warning, we need to, some of the positions are not even listed yet. So dynamic. So the best way is or approach me after this talk. It would be a pleasure. Chat, as well as about collaborations, by the way. And that's it. I stop here. Thank you very much for your attention. I'm super happy to take more questions. Formally, what? Sorry. At that level, we're not making a plasma. So, I mean, we're making a plasma of deuterium tritium surrounded by a liquid. It's at the liquid state. Yes, you're thinking of. Yes, okay, you're thinking of the electrochemistry. Okay. Yes, but okay, this is, so in electrochemistry, you apply an electrical current. In this liquid metal, we are applying indeed a current in the azimuthal direction for the sake of imposing radial forces, which is good. The only situation in which these free moving electrons might have a negative impact is, which I can foresee now, but I need to think more about the problem. But the only situation I can think of is a radial current, but it will have to be in the form of convective cells, unless, you know, no, it's mostly in the form of convective cells, unless you have a source in the sink. But whether it is, so these radial currents really have no reason. They're not applying a current in the radial direction. Neither it is forming under, you know, as a result of the interaction with the plasma. And if it does, the simple solution to that is to bias the solid substrate to minimize this current. We have these electrodes in the plasma anyway, again, to control the radial force. I wonder if any happens, so control the radial force, which means controlling the azimuthal J. If anything happens with the radial J, in principle, we could use those electrodes also to, you know, minimize those radial currents. This metal is definitely in the presence of a strong field. Maybe instead of electrochemistry, we should think about magnetochemistry. But electrochemistry, anyway, thought-provoking question. Thank you very much. It's we are so the short answer is yes, not as much as we need, in my opinion. One of our openings is actually for a material scientist slash chemical engineer slash corrosion expert. You know, it's a lot of yeah, as I said, material science, chemical engineering, and so forth, chemistry that needs to be addressed. We have, for example, a collaboration with the Savannah River National Lab in the US. They will measure for us these phase diagrams, because for lithium hydride, they are known, and they are approximately known for lithium deuteride and lithium tritide. But the detailed measurements, when you have the three of them, were never done before. And actually, there is a very interesting chemical physical calculation based on measurements with lithium hydride, lithium deuteride. You can extrapolate what will happen with lithium deuteride, lithium tritide. So there is a very rich field, theoretical and experimental, that has been, only the surface has been scratched. There is a lot of work to do. Collaborations, that some of them exist, but we definitely need more of them. Yeah. So from a business point of view, the fusion product will be ready here. So at the end of the electrify phase, the idea is to retrofit, the idea is to build a demonstrator together with public partners in a dismissed fission power plant. It could be a coal power plant, actually. This is to save cost and time. That will be our demonstrator, our working prototype before we can commercialize fusion. To be honest, I wasn't expecting this question from an audience of fellow physicists, but I have a slide in another presentation, but I will explain in words. So we don't see ourselves as operators of power plants. In fact, not even builders of power plants, but rather upstream in the supply chain, procurers of reactors. I emphasize reactors, not power plants. So the core, the Stellarator plus the heating systems, because there are other companies that build the confines, generators, switchyard, etc. So in the power plant, we focus on the reactor, or even at a smaller level on subsystems such as the HTS coils or the liquid metal solutions. So our ultimate goal, our product, you asked about commercialization, our main product will be these cylinders, okay? With HTS on the outside, liquid metal on the inside. Even though the cylinders per se will be ready in 3 years, the fusion relevant cylinders demonstrated that you can actually make fusion with them. They will be ready in a longer period of time. On the way to the fusion product, in terms of business, the idea is are magnets, and they can be used for a ton of applications. As you said before, medical and energy storage are particularly promising. Magnets for accelerators, synchrotrons, etc., are also another important one. So our idea is, okay, in 3 years, as soon as we prove these magnets, we can start. I don't even like the word selling. It's more about having impact on society. We can use them to benefit medical science, energy storage, etc. And in parallel, we develop something that will have an even greater impact on energy in a longer period of time. So it's a high temperature superconductor. Sometimes it's just a high TC, high critical temperature. Yeah, sorry, I said it quickly at the beginning. So yeah, high temperature superconductors. So this is REPCO, rare earth, barium, copper oxide materials, basically cuprate, exhibiting superconductivity at temperatures of the order of liquid nitrogen and higher. So hence the name high temperature superconductors. In reality, the property that attracts us is not so much the ability to work at high temperature, but rather to generate strong field. The three-dimensional problem is not just the temperature, but also the magnetic field and the current. And so in this three-dimensional space, low temperature superconductors like niobium tin, niobium titanium, they occupy a small corner. HTS, exactly, they occupy a bigger space, and the one axis that we are mostly interested in is actually the strong field rather than the high temperature. Exactly, yes, yes. It's a big, yeah, it's precisely that. It's a big inductor. But so when you design it, you design in a way to maximize the inductance. That's one aspect. But another aspect is how much current you can inject, and hence how much energy you can store. And the other axis in which these materials are very, have a huge operational space, current or current density to be precise. So if you can squeeze a lot of current in these inductors, or equivalently a lot of magnetic field in those volumes surrounded by the inductors, you can store a lot of energy. That's it. Oh, that's remarkably, well, it can be remarkably quick or slow. It depends on the L over R time of your circuit, the L of the inductor, and the R of your charging or discharging system. So it's very flexible, but it can be, if you need energy in short periods of time, you can have it. Similarly, if you want to store it quickly, you can do that. In fact, this is one of the most attractive features. The technology exists already. It's called SMES, Superconducting Magnetic Energy Storage. We have some innovative ideas on how to maximize the inductance on cylinders, on plates, etc. It has a lot of interesting ramifications in fractal geometry if you're interested. But the technology, it's a family of the basic idea, let's say, the basic principle has been around for some time. But one of the limitations, low temperature superconductors can only generate so much field. B, even if magically they could be operated at higher field, the forces on the inductor would be so high that your device breaks unless you have a huge supporting structure. But in the process of okay, here we go. In the process of minimizing the forces on the Stellarators, I mean, this minimization for the Stellarator is actually also good for energy storage. A torus, so the Stellarator is a torus optimized for plasma confinement. The energy storage system could be a solenoid, or it could be a toroid, preferably a toroid. And you optimize it with a different geometry for maximum energy storage, volume integral of b squared over 2 mu naught. You can do this optimization under the constraint of tolerable forces, just or you can create a figure of merit where, as you see here, the forces are part of the metric, or the energy storage system, just as we did for the Stellarator. So you can, out of many approximate solutions, you choose the one with minimal forces. So this issue of the system breaking apart due to huge forces is thank you.